Count down 5, 4, 3, 2, 1. And a homogeneous mixture is called a solution. Again, a homogeneous mixture is a solution. So next up, again, we're going to be looking at these terms right here. If we look at the next term, talk about a solution, we talk about the stuff that gets dissolved. And what do we call the stuff that gets dissolved? Is the stuff that gets dissolved a solute or is it a solvent? 5, 4, 3, 2, 1. Wow. The stuff that gets dissolved is a solute. So what I have up here is a number of different solutions that we're going to be looking at. And when you look at these, again, you're looking at these are considered to be homogeneous mixtures. And by looking at them, you can't tell that there's more than one substance in here. So, again, a solution is also called a homogeneous mixture. And the stuff that gets dissolved in here is called a solute. So if this solution, which it is, if the solution here is a salt solution, the salt would be called the solute, the water would be the solvent. So again, the stuff that gets dissolved is the solute, the dissolving agent itself is the solvent. Okay, next question, and if you are just coming in, get your Socrative app open here, please. If a substance is able to dissolve in a solvent, now we've covered this stuff before, everybody should get this one. If a substance is able to dissolve in a solvent, it is said to be soluble, or is it insoluble? 5, 4, 3, 2, 1. Thank you. They are soluble. Next up, again, we're going through these terms. Now, our next terms that we're going to look at are these two, the terms miscible and immiscible. Anybody know what it means if we say that something is miscible? If a couple substances are miscible with each other.
Maybe they're compatible?
Well, that's sort of it. They're compatible, but we need to be more specific. Well, if we talk about two liquids that are miscible in each other, that means they can dissolve together in any proportion. So again, the term miscible means that they can be dissolved together in any proportion. And the term miscibility refers to fluids. And fluids can either be liquids or gases. If we say that two substances are miscible with each other, again, that means they can be dissolved together in any proportion. And if we have liquids that are immiscible with each other, that means they cannot be mixed together in any proportion. So just think about them like mixing. These are mixable, these are not mixable. So it's pronounced miscible and immiscible. So our next question here is this. Which two liquids are miscible with each other? Select both. 5, 4, 3, 2, 1. Water and alcohol are miscible with each other. In fact, that's the basis of many people's Friday nights or Saturday nights, right? You mix together water and alcohol. Now, of course, not that you are all of age. If you're not of age, you don't know that, right? Okay, but water and alcohol are miscible in any amounts. And so if we have liquids that are immiscible with each other, which of these liquids be immiscible? And realizing that many of you just came from lab, this is something that we probably observed. And so we'll count down 5, 4, 3, 2, 1. And of course, water and vegetable oil. And I don't remember, I don't think you used vegetable oil in the lab, you might have used mineral oil, but the same thing. Water and oil do not mix together in any proportion. Okay, next up. Again, we're going through these terms. And for our next terms here, I think it's going on to aqueous and unaqueous. We skip over these. So if you want to talk about these terms right here, often when we think of a solution, many of us think of solutions as always being something that is a liquid. Well, that's only one type of solution. Solutions may also be gaseous. They may also be solids. And we use these terms here, we're referring to their final phase. And so when you use the term solution again, a solution is basically any form of homogeneous mixture. So that said, we should be able to figure out a gaseous solution. What type of mixture can we think of that would be made out of gases? And what are you thinking? Got something? What are you thinking? Air, sure, air. The air around us is a gaseous solution. It's a homogeneous mixture of nitrogen, oxygen, carbon dioxide, water vapor. When we look at the air, we can't tell that it's a mixture of a whole bunch of these different things. This here would be a liquid solution. This here is a salt solution. We mix together some salt and water, but the end product is a liquid. And a solid solution. Any ideas where we might find a solid solution? Many of you are probably wearing it. Okay, if you have like some gold jewelry or something, most of you aren't wearing pure gold. In fact, pure gold is typically not sold as jewelry because it's too soft. And so they combine with other things to harden that up. And so if you're wearing something like 14 karat gold or 10 karat gold, those things there are would be solutions, and it's considered to be an alloy. And any type of alloy or mixture of metals would be an example of a solid solution. And many of you are unknowingly wearing a solid solution in your mouth. If you have a dental amalgam, if you have a filling, which the fillings are called amalgams. If you have a dental amalgam, you've probably called them a silver filling before. And we've called them a silver filling in your line. It might have some silver in it, but anybody know what a very large component is of a dental filling?
Aluminum?
Not aluminum. It's actually a toxic metal.
Lead?
It's not lead. It's actually atomic number 80, Hg, which is mercury. And so that's blows most people away. In fact, I didn't even know that till about 20 years ago. But that's one of the reasons why the fillings are so pliable, and why a dentist, if you ever had them put in, they can pack those things in there, because mercury itself is a very soft metal and enables it to be packed. And when it's mixed with silver, and I forget what else is in a dental amalgam, it makes it able to pack it very tightly inside of there. And there's some people that believe that the mercury that's in those amalgams is in fact very toxic, and have gone in and have them removed. And scientists, dentists still use them because they believe that the research has shown that the mercury is not toxic to you when it's mixed in with the silver and whatever else that's in there. It basically brings its vapor pressure down to zero. And when we look at mercury, what's most toxic about mercury actually isn't the liquid itself. Most of us can handle, if we had the mercury in our hands and handled it, we'd be fine with it. Where it's most toxic though is just like any liquid will evaporate and produce a vapor. So like if we had a glass of water out, that water's going to evaporate and it's going to fill this room with water vapor. So if we had mercury in here, what would happen is that mercury would begin to evaporate and it would fill this room with some mercury vapor. And that's when we inhale individual atoms. And it's those individual atoms that are capable of being ionized real easily and the stuff that is most likely to be toxic. Now, not ever that, and this is one of those things where just because you read it doesn't mean it's true, but I've read more than one time that you could basically drink mercury and pass right through you, and most people wouldn't have any problems with it. It's the inhaled or vapor form that is the most toxic. And again, I would never recommend drinking mercury, but again, it's typically not that form, the liquid form, that's hazardous. It's the gaseous form. All right, next up. Oh, we have this one here. Everybody should get this one right. A solution in which water is the solvent. Is that an aqueous solution, or is it a non-aqueous solution? Aqueous or non-aqueous? So water's the solvent. We'll get your answers locked in here. We'll give you 5, 4, 3, 2, 1. All right, aqueous. Next up, again, we're going through these terms. So aqueous and non-aqueous are kind of paired. Solute, solvent, solution, these are paired up. These here. And so now we're looking at the terms dilute and concentrated. And so in this set of terms here, we have a solution that contains a relatively large amount of solute. We call it a dilute solution, or is that concentrated? 5, 4, 3, 2, 1. And that's going to be concentrated. So a concentrated solution is going to be one that if I pour in, again, a whole bunch of solute, so in this case the solute is salt, one that has a relatively large amount of that's going to be very concentrated. And if we want to dilute it down, what do we add more of? We add in water, we add in more solvent. So one that has a relatively large amount of solvent is going to be one that is dilute. Okay, I think that's it for these right now, so we'll take a little break on that, and I've got some stuff here I'm going to demo with these. So we have up here a couple solutions, and we are now going to make the distinction between saturated, unsaturated, and supersaturated. And we'll start by defining these terms right here. And we start with a saturated solution. And if you think of a sponge, if a sponge is saturated with water, what does that mean?
It has lots of water in it.
Has lots of water in it, exactly. Basically can't hold any more in there. So we said that a saturated solution is one that contains the maximum amount of solute that will dissolve in a specified amount of solvent at a given temperature. Now this here is a 3-variable definition. By 3-variable, that means that when we talk about something being saturated, there's 3 things we need to consider. First of these then would be the amount of solute. Next would be the amount of solvent. And then finally we need to consider the temperature. So again, when we talk about whether a solution is saturated or not, we need to consider 3 variables: the amount of solute, amount of solvent, and the temperature. So then if we went to an unsaturated solution, and we think about that sponge again, if we had a sponge that is unsaturated, what does that mean? It means that it could hold more water. So the same is true with an unsaturated solution. And we'd say this here, it is one that contains less dissolved solute than a saturated solution at the same temperature. And then we have a supersaturated solution, and we're going to use pretty much the same definition as before, except if we think of a supersaturated solution or supersaturated sponge, a supersaturated sponge is one that's going to be literally dripping with water. It's going to be so full it can't hold anymore, so the water is going to be coming out of there. And we call this type of solution supersaturated. And we say this is one that contains more dissolved solute than a saturated solution at the same temperature. And so now some key words here. We talk about these. These have to be dissolved solids here. So it's not simply that it contains the solute, but it says that the solute has to be dissolved. And then the other thing is, if we talk about a saturated solution as containing the maximum amount of solute, then it brings up the point, if this is the maximum amount, how could we have more than the maximum in a supersaturated solution? And so we're going to demonstrate that stuff here for you and give you some examples. And so I'm going to start here by looking at these two solutions. And right now I'm looking for my safety glasses. Here we go. And I have a couple salt solutions. And again, these salt solutions are ones that already have some salt in them. And I do have the webcam up here today. And so if we look at these solutions, simply looking at these, we can't tell that there's more than one substance in them. So what I'm going to do in each one of these here is I'm going to add some salt to them, and I'm going to try to add about the same amount of salt to each one. That looks like about 3 grams. And we'll come back to this one here. We'll add in about 3 grams. I'm just messing with you. I don't know how much is in there. But now, I'll go ahead and take these two solutions, and I'm going to shake them up. And then we're going to see what happens here to the solutions. So now after shaking these up, notice that one of these here, the stuff is dissolved. That's this one. And this one here, the salt that we added did not dissolve. So then the question is, which one of these here is the unsaturated solution? Which one of these here would be unsaturated? Would it be this one here or this one here? I know, it's a Thursday afternoon, but let's get your heads into these things. Which one is unsaturated? This one here? Yeah. All right, this one here. And why is this one unsaturated?
Because there's no salt remaining.
There's no salt remaining. So if it was unsaturated, that means it could hold more stuff in there. So there's more salt that could dissolve, and it did. This one here then originally must have been full. So if it was full, this must have been a saturated solution. So now, let's see here. Do I have this one? No, I don't have that one on the list of questions. So now, if this one was saturated to begin with, I now added some more salt into here to try to get that salt to dissolve. If I were to pour this liquid off of here now, would this liquid be saturated or would it be supersaturated? See, now that's a difficult question. It's actually not so difficult because according to this here, it says that a saturated solution is one that contains the maximum amount of solute that will dissolve in a specified amount of solvent at a given temperature. So did I do anything to the temperature to this in front of you? No, I didn't. And so when I tried to add more salt into it, that salt did not dissolve, which means that the solution here is still a saturated solution. Okay, so simply adding the salt in there, I'm not making any more dissolve into it. The key is that it must be dissolved solute. So if the solute didn't dissolve into it, then we cannot make this into a super saturated solution. So what I have up here then is some supersaturated solutions. And these are ones that I used this morning, and so I'm actually checking right now to see how these feel temperature-wise, because I want these to be room temperature. And so I had to cool this one off just a bit. And I think we're pretty good here at room temperature, but we'll go around here and we'll just verify that we do have these at room temp. So we can just feel the flask and make sure that the flask is about room temp. And what I'm going to do now is I'm going to try to dissolve some more solute into here. Now, this here is not a supersaturated salt solution. This one here is a supersaturated solution of this stuff. And let me get this stuff on the screen here for you so you can see it. I'll try to get this up here. I don't know if you can read that, but it is sodium acetate. Sodium acetate. These here are supersaturated solutions of sodium acetate. And what I'm going to do here now is I am going to add some sodium acetate to these solutions. We see that it is, in fact, in the liquid state right now. And I need my spatula for this. And I want to make sure that the spatula is nice and clean. And I am going to take out 1 crystal of sodium acetate and try to get that to dissolve into here. Now sometimes I'm not successful getting 1 crystal, sometimes I get more. And it takes a while just to get 1. Sorry about that. Here we go. I think I have a crystal on here. And so, I don't know if you can see that very, very, very tiny speck right at the end of the tip of the spatula. But what I'm going to do now is I'm going to take that one tiny speck and I'm going to drop it into here, and we'll watch what happens to the solution. So of course now we're watching these nice crystals grow when I do that. Now, the question is, what do you think happened to the temperature? What do you think happened to the temperature? This is where it's kind of fun to make a prediction. Did you predict that the temperature increases, decreases, or stays the same? Get your answers locked in. And once you see your neighbor have your answer locked in, you go ahead and pass that around. You can pass that back here. I've got one more that I have, and this one here I'll set down, and you can just go ahead and feel that flask as it comes around. Now, again, this here is another supersaturated solution of sodium acetate. And what I'm going to do with this one, so again, this is a supersaturated sodium acetate solution. What I'm going to do with this one here is I'm going to, instead of putting sodium acetate into it, I'm going to try adding some salt. So, no, that's a little too much, more than I want. That should be enough. So what I'm going to do now, and you should be able to see into this flask here, I'm going to go ahead and put the salt into here. Watch what happens when I drop the salt in. And you should see that that salt winds up sinking right to the bottom. So why do you think that the salt did not dissolve in there? Well, again, it's supersaturated with sodium acetate. It's not supersaturated with salt. So again, this is a supersaturated sodium acetate solution. And you saw me dump in a whole bunch of crystals there. So what I'm going to do now is I'm going to come back here and I'm going to take just one crystal of sodium acetate, And again, it's kind of hard with the glare for you to see it, but I have one crystal on the tip there. And I'm going to go ahead and drop this one crystal in here, and we'll watch what happens when we do that. Again, we're saying go right here. And you can see that this is that. Now, what happened to the temperature? The temperature actually went up. And hopefully you didn't change your answers here. We'll see that most of us probably predicted that the temperature would have decreased. Now, this goes back to something that we looked at a couple class periods ago. And we had a diagram that looks something like this. And we said that when liquid changes into a solid, that process is one that is exothermic. And so usually when we see something like ice freeze, it happens over such a long period of time, we can't actually monitor what happens. When we talked about one of the things that we do is with citrus trees, we spray them with water, and spraying with water, when that water freezes onto those trees, it's actually releasing heat that prevents the fruits from freezing. But this is one here now that occurs very rapidly. We can see that transition occurring from a liquid to solid. It definitely gives off some heat. Now, can you think of a use for something like this? Well, some of you have actually used this before, and one of the ways that you may have used it before is with one of these. Anybody know what these things are? They're hand warmers, okay? And I accidentally just triggered one of them here. So it means I only have 3 of them. So I'm going to, Gabby, if you would like to take one here. Just be careful on that one. And and we'll come back here. And what we're going to ask that you do now is there's a disc inside of there, and I want you to hold it up high enough so that everybody can see around you. So don't do it yet, but you'll see there's a metal disc in the bottom of each one of those things. And the packets that they have are supersaturated solutions of sodium acetate. And what they're going to do is we're going to ask them to create a seed crystal inside of each one of those packets. And once they create a seed crystal, what's going to happen is that the sodium acetate that's in that solution is going to crystallize out just like they did right here. And to make a seed crystal, what they're going to do is there's a metal disc in the bottom. They simply press on that metal disc. When they press on that metal disc, you're going to hear a click. And you can go ahead and do it now. You'll hear a click. And once you hear that click, hold that packet up so that people around you can see what's happening. And you see now that the stuff is crystallizing around there. If you feel the packet, how does that packet feel? Warm. And so you know what that's used for? That's a little portable heat pad. Little hand warmers. Okay? So, and I had another one here that just triggered when I was holding it. I held it on the wrong end and I triggered it myself. But if you feel it now, that's one of the uses of a supersaturated solution. Okay? So, turns out that there's 2 types of portable hand warmers. And one of the types of hand warmers is what you just observed right here, and it is a supersaturated sodium acetate solution. I don't know if all of you got to see the salt that was passed around. Anybody did not get to see the salt crystals here? Okay, so have you pass it around and look at the salt crystals. And once you look at it, pass it back to anyone else that may not have seen it. I'm going to grab it here. But if you look at the shape of those crystals, what shape did those crystals have? They're going to be squared. Three-dimensional would be called cube. Okay? So it's cubic. And the reason why it's cubic, anybody else not see these? You guys do? Okay. Now the reason why you see these as being cubic is because down on the atomic level, the sodium and chloride ions actually form cubes. And so what will happen is it builds up in 3 dimensions around that sodium chloride crystal. So now, if you think back to when we were demoing these, remember that in order for us to cause this crystallization to occur, this here was a supersaturated sodium acetate solution. In order for this crystallization to occur, I had to drop in a C crystal of sodium acetate. And so I dropped in 1 crystal of that sodium acetate then. What happened is all of the excess crystals came out of that solution, all the excess solute. When I tried to drop the sodium chloride into that supersaturated sodium acetate solution, what did we observe then?
Nothing.
Nothing. Because again, it was supersaturated with sodium acetate and not with sodium chloride or salt. And that's because every substance has a different shape of crystal. In the case of salt, salt has these nice cubic crystals that you saw underneath the magnifying glass, but sodium acetate has more of an oblong crystal shape. And so it does not provide the right surface for the sodium acetate to build up off of. So I dropped that into there, it simply sank to the bottom because there's no way for those ions to build up on there like it was salt. Now if I had a supersaturated salt solution, then we would wind up seeing salt crystals that would form. But there's part of the reason why I can't make a supersaturated salt solution, and we'll talk about that in just a moment. But one of the uses then is those portable hot hand warmers that we have. Now the other type, and I don't have these out here today because it doesn't really apply to solutions, but since somebody asked in my morning class, I'll mention it here today. The other type is one that contains iron powder, salt, and water. And those are the ones, yes, Gabby?
So like when you make rock candy?
Yes.
Is that kind of like the same way?
Yes, rock candy is a perfect example of a supersaturated salt solution. And honey is another example. If you ever had honey and you put the honey in your shelf, you don't touch it for a long time, what happens to that honey?
Turns solid.
It turns solid. And nobody likes to spread solid honey on their bread, so what do?
Microwave.
You microwave it, or you put it in a pan of water, you get it all to dissolve, and then you can spread your honey on, and then you can leave it on the shelf, and sometimes something will trigger it, and then it will crystallize again. But rock candy is another one there. And the key to all of them, and I might as well just show this to you here right now, the key to all of that is these solubility curves. And turns out that if you look at these solubility curves, this is a plot of the solubility, that is the amount of stuff that will dissolve in water at given temperatures. Sodium chloride or salt is this one right here. And you notice that it's one that does not change a whole lot. Its solubility does not change a whole lot with temperature. And so for a demo like this, it wouldn't work very well. Turns out that sodium acetate isn't on here, but if I had one for sodium acetate, it would start out really low and it would get super high really fast. And sugar is another one that starts off really low and winds up super high. So if you want to make a rock candy, what you do is you dump a whole bunch of sugar into water, you heat it up until what happens?
So it's like dissolve and something.
Right. Then you get it until it all dissolves, and once it's all dissolved and heat it up, then what do?
I put string in.
You put string in, but after you heat it up, you don't leave it hot, then what do? You cool it back down. And that's how you make a supersaturated solution. You basically keep adding more and more and more at a higher temperature, and then you cool it back down. And when you cool it back down, then it's actually holding more solute than a saturated solution at the same temperature. And then to make that rock candy, then you suspend that string in there. You suspend the string in.
And you tie other pieces to it.
Yep.
And
Exactly. And then the sugar will crystallize around that sea crystal. So that's an excellent excellent example of that. So, but again, the reason why sugar works and can make a supersaturated solution is because it has a very steep solubility curve when we make it. Now, the other type of hand warmers, getting back to these here, the other type of hand warmer is one that contains iron powder, salt, and water. And that's actually the one that most of you are probably familiar with. Let me ask first, have anybody used these hand warmers before, this type? Anybody used a different type of hand warmer before? And what type, I mean, how would you describe the packet the other ones come in?
It's like small, brown.
Yes, and is it plastic coated or is it, feels more like a cloth, right? Okay, so the other type of hand warmer is one that has kind of cloth outside, and the one that has a cloth cover on it is this type right here. Now you wouldn't believe how simple this reaction is as well. Basically what happens in this reaction is this. Iron reacts with oxygen to make iron 3 oxide. That's all that happens in these packets. But now, what happens is you get those packets. In order to activate them, to make those other packets warm, what do you have to do? You shake them up, but before you shake them, what do you need to do? You need to open up the package. And you basically, when you open up that package, you're going to expose that package to oxygen. And once you expose it to the oxygen in the air, the iron in that packet begins to react with the oxygen in the air. And that's why it's cloth, because the oxygen has to move through the cloth outside. And then it will react to form iron 3 oxide. Well, we're all familiar with iron 3 oxide, whether you know it or not. This reaction happens around us all the time. What is this process called? And where do we find iron 3 oxide or iron oxide? Well, another name for this is rust, right here. So basically, when iron gets exposed to oxygen, it rusts, right here. And what do you think the salt is for? Well, it's a catalyst. It helps it rust. Just like our cars in the winter, right? When we drive over the salt-covered roads, it gets up on our cars, and because our cars get covered with salt, it begins to rust. And it speeds up that reaction between the iron and the oxygen to form the rust. So basically in those packets, you're making rust. You're making rust by simply opening it up to the oxygen in the air. The little bit of salt and water that's in there then helps that oxygen react and forms that rust. It turns out that that process is an exothermic process. Now, the nice thing about these is we can reuse these. In fact, I used these for my morning class today. If I wanted to reuse them for this afternoon, what did I do to them? Well, I threw them into a pot of boiling water, and I just heated them until they dissolved, and I set them on the counter, and then I allowed them to cool, and I brought them in here for this afternoon. That's all I had to do, was just heat it up until it dissolved, and we can use this, and we can use this over and over and over again. Now the other type, the ones with the iron, these aren't reusable because once we use up all the reactants are gone. But we can actually make these here last longer. How do we make these last longer? Well, how about if you only need to use it for an hour? What do you do to those packets? Well, if you haven't done it yet, you can just put them into a Ziploc bag, something to basically cut off the source of oxygen. And once you cut off the source of oxygen, you can then use them longer. Take them out the next time, re-expose them to the oxygen, and then the reaction will begin. Now, this particular reaction right here is one that I've had a lot of experience with over the years. In fact, again, these are ones that I used in my morning class here today, and part of the reason why I had the ice here is because they weren't cooling down fast enough right before class. So right before class, I put them in the ice water to speed up the cooling so they would in fact get down to room temperature. But back when I started my teaching career, I was teaching high school, and I didn't have nearly as much extra time then as I do now. And it's not like I have an abundance of extra time now, but I didn't have time to do these, and I had to do the lab prep myself. So we used to have a thing called snow days. And I was teaching down in a small town of Waseca, if you know where that's at. And we had the snow day, and I said to myself, wow, this would be a great day to redissolve my sodium acetate solution. So I put the hot plate out in the front bench in my classroom. I put the flask onto the hot plate, and I turned on the heat. My buddy came by and said, hey Lance, how'd you like to go to lunch? I said, sure. So off to lunch we went. About an hour later, I come back into the school, and walking down the hallway just reeked of vinegar. Now, remember, the stuff that's in here is sodium acetate, and vinegar contains acetic acid. So I knew right away that I was in trouble. What had happened is that this thing had overheated. In fact, this thing here, just think now of heating that honey on the stove. Let's say you poured a bunch of honey into a pan and you started heating it. How evenly do you think honey heats? Real even? No. It bumps and boils, it spatters and everything else. And the same thing happens to this. It's a very viscous solution, and this neck on the flask kind of acts like a barrel of a shotgun. Okay? So this sits on the desk, and it was underneath one of these vents here. And so what happened, it kept shooting that stuff up into these vents. And when it hit the vents in the ceiling, it started crystallizing immediately. And a lot of that stuff was coming down, was crystallizing on my front bench. So it's like, I was really kind of ticked, but I cleaned everything up. And next day I came in to school, and I saw all these little droplets on my bench. I couldn't figure out what had happened. But I wiped it up, and then I noticed I had these big white streaks all over. Come in the next day, I see these little droplets on my front bench. I wipe it all up, and then I have these white streak marks all over. And this process repeated itself for 3 months. Every morning I'd come in and I'd see these little white spots on there. I'd wipe it up, and then I'd see my white streaks. I have to take water and wipe it down again. Now it turns out here's what had happened, is that it shot it up in that vent. Every morning the ventilation kicked in. It knocked a few of those crystals down onto my bench. Sodium acetate happens to be a hygroscopic substance, which means it absorbs moisture out of the air. So this would knock the flakes down. The flakes then would form these little droplets. Because it was absorbing moisture out of the air, I'd wipe it down. That would expose a larger surface to the air. That would form the white streaks, so I didn't have to take the water. And again, repeated itself for 3 months. So I was really frustrated with that. So next year, we had another snow day. I said to myself, this would be a great day to redissolve my sodium acetate solution. But I'm not going to let happen to me what happened last year, right? So I went to my office, put the hot plate in my office, put it on there, cranked up the heat. My buddy came by and said, hey Lance, how'd you like to go to lunch? Sure. We take off for lunch. About an hour later, I come walking down the hallway, just reeks of vinegar. And I go into my office, and my office is just covered with all sorts of good stuff. And so it earned me what's called an ah shit award, because I like to say that when something bad happens. And so anyhow, I learned my lesson, talked about this for years. My students laugh, ha ha ha, whatever. But now, I've got more students here, and I'd like to demonstrate this on the same day. So, if I want to demonstrate on the same day, I don't just have this one, I actually have a whole bunch of these, like 4 of them, so I can use a couple during class. If I don't have time, I can use a couple more. And so I have 4 of them here, and of course, you know that this last Tuesday was the last day to withdraw, right? Well, one year, the last day to withdraw fell on the day that I demoed this stuff. So I went to the prep area, I set all 4 on the hot plate, cranked up the heat. I'm sitting there and talking to students in the office about dropping everything. Pretty soon somebody comes running, what's going on in the prep room? What's going on in the prep room? And so we had 4 of these things that shot off in the prep room. And if you go back, that was all like 10 or 12 years ago. If you go in there now to this day, you can still see, like in the light fixtures and everything, there's some splattered sodium acetate that sits up there in the ceilings. So, I was banned from ever reheating these. I am allowed to cool them now, but I'm not one that does any of the reheating anymore. All right, that's my story, and I'm sticking to it. Any questions? All right, next, solubility. We talk about the solubility, and we've kind of alluded to what these graphs are here on solubility, we define the solubility like this. We define it as being the maximum amount of solute that may dissolve in a specified amount of solvent at a given temperature. In fact, you're saying to yourself as you're writing this down or listening to this, this sounds very much like the definition for a saturated solution. And it is, because we define the solubility as the amount of solute required to make a saturated solution. And in here we have to define three quantities. We have to define the amount of solute, the amount of solvent, and the temperature. And so it's a three-variable definition. And if we come back to this graph and look at it, you'll see that this is a three-variable graph. What it is we have the temperature here, and it talks about the grams of solute expressed per 100 grams of water. So the temperature, the amount of solute, the amount of solvent is all given here on this graph. And so as we look at this graph, we also look at the key over here. The ones that are solid lines, these represent solids. The ones that are dotted lines here represent the gases. Again, the axes, if you can't see it, this is temperature on this axis. This is solubility on the vertical axis. So this takes us to two more questions on the Socratic map. In fact, we might knock off all three in a row here. We examine these solubility curves. When the temperature increases, the solubility of solids tends to do what? So again, as we increase the temperature, what happens to the solubility of solids? 5, 4, 3, 2, 1. And we see that they tend to increase. Next one here is with regard to gases. When we examine the solubility curves, when the temperature increases, the solubility of gases does what? So as temperature increases, solubility of gases will do what? 5, 4, 3, 2, 1. And we see that they decrease. So again, looking at the data, we see that with solids here, solubilities increase with an increase in temperature. Gases, these dotted ones, solubilities tend to decrease in the temperature. And again, we use the terms just to cover our bases. It's not always the truth. We say that it tends to, because with every rule there's often some exceptions to that rule. And we saw at least one of them here with the solids. The sodium sulfate, for example, we see that its solubility actually decreases. But the general rule is that solubilities for most solids tends to increase with an increase in temperature. So when we read the actual solubility, now as far as to explain it, explanation here works something like this. First of all, as we increase the temperature, what happens to molecular mobility, or the speed of molecules?
It increases.
It increases, right? So the reason why solids are going to become more soluble is that they want to increase their mobility. They then go from the confined or restricted solid phase, where they stay in a very organized pattern, to one that is more disorganized in that dissolved or aqueous state. So that's simple to describe. So again, as we increase the temperature, we expect it to become more soluble, because that allows the solids to become more mobile by going into that aqueous phase. We actually use the same explanation for gases. The reason why they decrease their solubility with an increase in temperature is because if we want them to be more mobile, gases then would escape the dissolve phase and go into the gaseous phase. By going into the gaseous phase, they're even more mobile, and they have that ability to move. So when we look at the data itself here, we want to express solubilities. Here's how we would write out the solubilities. We would say that the solubility of, and let's work with potassium nitrate, we would say that the solubility of KNO3 is, and we give the solubility, we have to define all three variables. And what we'd say is this: let's say that we wanted to define the solubility at 20 degrees Celsius. We would then look at where that potassium nitrate crosses, which it appears to be about right here. And we then say that the solubility of KNO3 is about 32 or 33 perhaps. We could then say that it is 32 grams of KNO3 per 100 grams of water. And then we have to define one more variable, and that would be the temperature. And this is at a temperature of 20 degrees Celsius. So again, when we give the solubility, we have to give the value of all three variables in the solubility. And if we wanted to do it, say, at 70 degrees, let's say that we looked here at 70 degrees Celsius for the KNO3, and I'll put the temperature scales up here. This is 10, 20, 30, 50, 60, 70, 80, 90. We'll go every other one here. And so this one is on your Socrative app. If we wanted to give the solubility of KNO3, we can just put in a number here. I'll put the graph up at 70 degrees Celsius. And if you need me to zoom in, I'll zoom in here a bit. 5, 4, 3, 2, 1. And we should have come up with about 139, 140, thereabouts for the answer. Okay, so right around here, looks like it's just maybe a little bit under 140, about 139 grams of KNO3 per every 100 grams of water. And so we'd write that in something like this. If we want to show its solubility, we'd say that it is 139 grams of KNO3 per 100 grams of water at 70 degrees Celsius. So again, with the solubilities, we'd specify the quantity of all three variables in the mixture. Now for gases, notice that the maximum solubility occurs at what temperature? Always. Occurs at a temperature of 0 degrees Celsius. And so if we wanted to look, for example, at a solubility curve, let's talk about the solubility of dissolved oxygen. In the solubility curve of dissolved oxygen, all that really matters is that this temperature here is 0 degrees Celsius, and if this axis here is solubility, this solubility curve is going to look something like this, where the dissolved oxygen has its maximum solubility right at 0 degrees Celsius. And so now we were talking the other day about, and we kind of were rushing at the end of the hour, but water is a very unusual substance in that it has a density in its solid phase that is actually less dense than its liquid phase. For most substances, that isn't true. For most substances, the solid phase is actually more dense than its liquid phase. But because ice is less dense than water, that means that ice is going to be found where?
On the top.
On the top. And so as a result then, our lakes don't freeze solid. The ice forms on the very top and it stays there. It doesn't sink to the bottom because, of course, if it would sink to the bottom, eventually the ice would wind up filling up the lake. The lakes would freeze solid. So the other amazing thing here is this, and that is right before that lake freezes up, it's going to contain the most dissolved oxygen it could possibly hold. And so once our lakes freeze up here in Minnesota, again, the ice is on top, and it's basically locking in oxygen into that lake at the largest solubility it could possibly have. And so that's one of the reasons why aquatic species are able to survive through the winter, is because of the high amount of oxygen that is dissolved in that water. Now, of course, if it's overpopulated, or if we have long winters, or if we have a lot of snow and it covers up the ice, sometimes that amount of oxygen gets depleted in there, and the DNR opens up what's called promiscuous fishing season, which basically enables you to take as much fish as you possibly can take out of the lakes at some point. And very often they will aerate those lakes to make sure that all of the fish don't wind up dying. One of the other things I did here as an undergraduate student is I worked, it was kind of an internship at a coal-fired power plant. And this was down in Iowa, and the power plant was on the Missouri River. And turns out that the power plant kind of sits up here on the hill, and the river sits somewhere down below. And what happens is this. We have something that is called thermal pollution. And thermal pollution is actually something most of us don't even think about, because when we think of pollution, we often think of there being chemicals or something that makes the air bad or makes the water bad or whatever else. But what does thermal imply?
Heat.
Heat, exactly. And so this is heat pollution. And I don't know if any of you have ever been up by the Monticello power plant. Okay, nobody in here? Okay. So if you're in there, you go look up there in the winter. You'll see the big mounds of steam coming out of the power plant. In fact, you can see that all parts of the year, but especially in the winter, there's huge amounts of steam that come out of there. And that's because all power plants, whether they're nuclear or coal-fired or whatever else, they take tremendous amounts of water to cool down the turbines that are found in those power plants. Well, of course, if you heat up water, that water then eventually has to be cooled before you return it somewhere else. Well, when you're going to return it, you're probably going to return it to a river if you're there. Well, you see now that causes a problem, because if you return it to a river and that water is warm, what does that do to the solubility of the oxygen? Causes that solubility to go down. If it goes down, what is that going to do to the survival of aquatic species?
Also go down.
It's going to cause it to go down as well, because most of those species, like fish, they require dissolved oxygen. Okay, so that's a big problem. In fact, one of the things that wasn't considered a long time ago is when developments went up around trout streams. Anybody fish for trout around here? Okay. Anybody know what kind of water trout requires? Really warm or really cold? What is it? Really cold. Trout streams are really cold. They come from spring-fed streams, rivers that come out of the ground. The water is really cold, and trout can only survive in that really cold water. Well, when developments go in, they put in what's called storm sewers, and all cities have storm sewers. And basically what it is, if you go along a side street, you're going to see these little grates along the curb there, where when it rains, the water flows down into those gutters. And anybody know where the storm sewers wind up draining to? They go out there, to the river. Okay? So now, here's where the problem lies. Usually, especially in the summer, when we get storms, it follows what type of weather? Stuff where it's really, what?
Hot.
Really hot, exactly. And it's often been sunny, and the pavement gets really warm. So that rain comes down then onto that warm pavement. And once it gets onto that warm pavement, if we get a lot of rain, that then is going to go in the storm sewers, and those storm sewers will discharge out into the river. So now you have all of the pavement which has been cooled down, but that heat's all been transferred into the water, and that water has been moved out to the river. And of course, then the temperature of the river will go up, and as a result then, the dissolved oxygen will go down. And so this is especially critical around trout streams. where now you cannot divert any water into trout streams. You'll see if there's a trout stream anywhere nearby, you'll see the fences up and everything to prevent any type of stuff being diverted into these trout streams. They have to divert them other directions to keep that warm water out of there, because you can basically kill off all of the trout in the trout streams if they wind up with the warm water. So in the power plant, what we did was this. Coming out of the power plant was kind of like a cascade. It looked something like this. Little jagged edges. And then when the water came out of here, the water flowed down those grates and basically cascaded like a bunch of waterfalls. And the whole idea when they come out of the power plant was to do what? Actually, two things. One would be to cool the water, and the second thing would be, by cascading down there, it would be adding in some more oxygen back into the water itself. So it has the effect of aerating it. Just like when we turn on this faucet here, you see the air bubbles in here. That's because there's a screen that sits up in these faucets, and the whole idea is to aerate that water when it comes out. So the idea here then as well is, as it goes down, is to aerate that water and to cool it down as we come out, in an attempt to build up the amount of oxygen. All right, so that's it on solubility and solutions.